So yet another good talk about boot time optimizations. We can get that at least once a year. So actually this is almost the same talk as I gave at the Automotive Linux Summit. So if you were there, it's not you don't have to see that. So quickly the mandatory advertisement. So we have denominated. Basically we are a service company. So we are doing DSP and driver development. Our company is also doing hardware development. We are trying to do system optimizations, like obviously boot time optimizations. We are also doing applications, but not so much, and a lot of other stuff. So basically, I'm at Tadinio, I'm the Linux and Android team leader. So I'm doing mostly Linux stuff because there's also a part of the company that is doing Windows stuff. So one of our customers came to us and wanted to boot fast. So what was the use case? Basically, they were trying to put Linux and the entertainment system of a good known car company that is making red cars that are going pretty fast. So the requirement was to reply to a CAN message. Basically, their board was not powered at all. So when you were powering on your car, basically there was already one board that was getting the CAN message, and that one was powering on another board, and that was the board that was running Linux. So then you had to reply to a CAN message. So basically it was a keep alive or more vitality message. So basically, are you alive? And you had to reply yes. So we had something like 500 milliseconds from power on. I will emphasize on power on because actually your hardware is doing a lot of stuff between the time you're putting power on it and the time it will run the first instruction. So you will see. So basically it's taking almost 120 milliseconds on an IMX53. So that's quite a lot. So we had 500 milliseconds, so basically we just have like 380 milliseconds to reply on it. So we had to be quite fast. The first answer we had was like, okay, we just have to do that in the bootloader. And they replied, yeah, but we would prefer to do that from Linux. So we tried to do that from Linux.
Why we do that in a car?
Yeah. So also one requirement was they wanted to keep almost all the functionalities they had in the kernel. So like 3D acceleration, I don't know. They wanted to be able to do what Linux makes you able to do. We had also another use case, so that one more for fun. So basically we wanted to boot an OpenGL application. So we wanted to boot the full Linux with OpenGL and OpenGL acceleration as fast as possible. So we try to still keep let's say real use case. So we decided to take just one OpenGL example that was already built for the platform. So the platform was an IMX6, and we decided to not modify it. Okay, so basically the use case would be we got a customer, he comes with his application, and we try not to modify the sources. We just try to optimize the boot. So where do we stand? So where do we start? So two use case. For the IMX53, it's taking almost 20 seconds to boot. Okay, so it's just the original Freescale image. And for the IMX6, you will have some issues. So you see, it's taking between 15 and 53 seconds Because actually there is a bug in the MFC driver, so sometimes it's just goes there and waits for I don't know what, and you go forward. But yeah, expect something like 15 seconds. So, what did we try? So we tried a lot of stuff, so I will present you what we tried. First, the first thing everybody does is just to set LPG. So basically just setting the loops per GP. You will always earn 250 milliseconds doing that because that's the time the calibration loop is taking. So it still is quite good, but yeah, if you have 15 seconds, it's still quite good. So then you will strip init. So basically what you want to do is just to start the minimal set of application you want. So maybe just the critical application you have and start from there. So basically you just try to start as soon as possible. So either you run in on level 1, I don't know, maybe the first thing you start in RCS, depends on. What we did is just we rewrote init and we say, okay, init is our critical application, so it will just be the first application that is run by your kernel. Then, so for flash storage, you can try a lot of stuff. On those boards, we tried NAND, NOR, and SD card, and actually we were the fastest with SD card, so that was not really expected. We were expecting that NOR would be faster. But yeah, SD card was the fastest one, so we used class 6. There is an issue in using class 10 SD card, as you will see on the leader website. Class 10 SD cards are the most common ones that are counterfeit, so you will probably get a class 2 card or something like that. So you will really have to benchmark it. So we also tried various tool chains. So not all tool chains are created equal. Basically what I mean is that depending on your tool chain, you might win like 10% of performance. So yeah, that's really good. The only issue there is that the fastest one was the linear one, but at some point in time, when you will see, we wrote a new bootloader, but when we combined it with the linear tool chain, it didn't work. So we had to go back to another tool chain. So also, one of the first steps you want to use is just to remove as much as possible from the kernel. Okay, so the less features you have, the smallest your kernel will be. And then, if it's smaller, then it will be faster to copy from storage to RAM. So obviously, it will move faster. The only issue is that, obviously, in our case, our customer wanted to keep all the functionalities. So sometimes you can just put all your functionalities as modules. It's not always possible. Like the blocks system or that kind of stuff, you can't put that as a kernel module. You just have to combine it in or not. So some stuff you can pay attention to is just, okay, once you're in production, you don't care about debugging, so maybe you can just remove your console. So console port and your output, you just disable that. It will get a lot faster. Then obviously print case and debugFS, so you can remove that. I will really advise using config CC optimized for size, because the smaller your kernel is, actually it's on one embedded platform, it's usually more efficient to optimize for size than to optimize for speed, because as your code size is smaller, it will stay in cache. It will stay in cache longer, so you won't have to make a lot of memory access. So you can also try different memory allocators. So usually slurp is the fastest one. And you can also remove call scenes, because it's only used if you want to debug. So as I say, it's not always possible to do. So that may not be what you want. Just take a lot of features from your kernel. So you can use modules. You can also use something that is called deferred init calls. That's really that's a simple patch. It's really easy to apply. Your kernel will still be bigger than if you didn't have the functionality, but at least you will be able to start it. And what you can say with deferred init call is just to say, okay, those init calls for those subsystems or those drivers, I want to execute them when I want. So basically, you will say, I will execute them once my application is ready. So it allows you to boot your kernel with a minimal set of features, start your application as soon as possible, and then say to the kernel, okay, continue your initialization. That's really useful. So you can get the patch and everything there on the Linux.org website. So also kernel compression, you can try to play with that. There is no, I would say there is no fixed answer to that. Usually none and LZO are the best one. Nobody is using GZIP anymore, I hope so. So you have two things. So if you don't compress your kernel, it will get bigger, so you will take more time to load it from storage to RAM. With LZO, the issue is that it will get smaller, so you will take less time to copy it from storage to RAM, but then you will have to decompress it. So it really depends on the horsepower you have on your CPU. Basically on the IMX6, it was almost the same. It was just a matter of 1 millisecond or so. So we just say, okay, we don't compress the kernel and we have plenty of space on the house storage and it's fine. So also SMP. SMP actually it's quite slow to initialize. On that board you have 4 cores. So basically booting with 4 cores is taking like 1 second and 200 milliseconds, something like that. And when you boot only on 1 core, you go to 800 milliseconds. So you earn a lot of time just booting on a single core. Actually, what you can do is just to say to your kernel, okay, I want to compile it with SMP, but don't start the core yet. Okay, just boot, and then once my application is started, you will hot plug your CPUs. That's something that's working. You can also try to play with memory call. So basically, you just say to the board that you have less RAM than you actually have. The less RAM you have, the faster you will go. Actually, it's just an issue of initializing the slab and stuff. Unfortunately, we don't have yet a mechanism to be able to hot plug RAM afterwards. So you will be stuck with just a small amount of RAM. Maybe it's simple to do so. I have looked at that. So, like I said, we completely get rid of U-boot. So U-boot is basically taking a lot of time to boot, to start, so we just got rid of it. We started using something that was written like in 2005. It was called ARM kernel shim. It's just a small bit of code that you prepend to your kernel so that it will be able to boot. Actually, we had to modify it a bit so that it will boot on free-scale platforms, and then we had also to do some crypto stuff so that the kernel, at least to sign it and some stuff, so that the CPU will recognize that our final image is bootable. So what it's doing is just configuring a few registers and saying to the CPU, okay, boot now. And also you have to pass at 8 tags, so that's something you have to do to the kernel, so like the command line and stuff. What's really nice with free-scale CPUs, so I'm not affiliated with free-scale at all, but what's really nice is that you can just say to from code to okay, I want to load that image from that storage and just to put on it. So it can get really easy to put on whatever image you want. So we had some issue with our custom bootloader. So the main issue was that on the IMX53, you actually have to talk with a PMIC, so the power management IC, to set your final frequency. And unless you lose that, you will run at like half your maximum frequency. So, and there are quite a lot of stuff like that that are still done in U-boot. For example, you will have quite a lot of pin boxing, that kind of stuff that is still done in the bootloader and that is never done in the kernel. So our question is that should we take that and put everything in the kernel? Should we mainline that? I would say yes. So we'll have a discussion today at actually it's at 6, at 6:15 in Zafir. So if you want to join the discussion, feel free. So okay, we saw our bootloader, we saw the kernel. So now we'll focus on the optimization you can do in the whole file system. So, like I said, you may not be able to optimize the customer application. So maybe the customer will come and say, okay, the application is our stuff, we won't have to see the sources, we don't want to touch it, we know that's working, so it's just there, don't touch it. Sometimes you don't even have the sources. So sometimes you may not even be able to recompile it. So for example, if you want to change your libc, maybe you say, okay, you use glibc, we want to get rid of glibc, we want to use microclibc. Sometimes you can't do that because the customer doesn't even want you to recompile. So basically that's what we did with the IMX6. We just say, okay, we just take the binary and try to optimize for So you may also need a lot of different applications, or you may have a lot of dependencies on a lot of libraries, so you may not be able to optimize the size of your code file system. So what we did there is that we are using an init FS. So basically we are just taking the critical application, the one you want to start as fast as possible, and we are just putting it in the init FS. Okay? So in that init FS, we are just putting what's necessary for your application. So, and we are trying to root only that. And then afterwards, you know that your application is loaded, that it's running, it's ready, and then you use switch root to your new code file system. So basically, in our init FS, what we did is that we used microclibc, so that it gets smaller than glibc. And also, that's one trick that I don't know if a lot of people know it, but there is a script that is called mklibs, and you can also find it like it will be called mklibs and .cross or something like that, or cross compiling. It will try to strip your libraries. So it's quite smart, and you just pass it a path to your code file system. And we'll try to scan all the binaries there. It will try to get all the symbols that are not used and remove them from the libraries. So your libraries will really shrink with that. That's really good. So I will present our final solutions. So basically on IMX53, what we did, so the one that was going to the car. So we were booting from SD card. We were using our custom bootloader. We stripped the kernel quite a lot, but not all the functionalities, because we, as I say, we had to retain all the functionalities. So basically, we removed a lot of stuff that was compiling, and we were compiling everything as module. And then we wrote a custom init. That's where. So the custom init was just the critical application itself. Okay. And so in that case, it was a daemon. And then it will, that application will call deferred init call once it's ready. So your kernel will continue to boot. And then we're using switch root to switch to our new rootfs and exec the final init. So the final file system was on the SD card, but as we were running from init.fs, the MMC driver was not compiled in. So the MMC driver was actually only loaded once the application was started. That's good. So on the IMX6, we are booting from SD card, still with a custom bootloader. Okay. So we also stripped the kernel quite a lot, and then we removed everything we are not using. So basically, the only things that are left are display and that kind of stuff. There is not even input or anything for afterward. And it starts a custom init, but it's not that big, and it will launch the OpenVG application. Like I said, we didn't change the binary. On that one, we stripped the rootfs using nkbit, and our final image is taking 5 megabytes, something like that. And we have 3 megabytes for hardware acceleration and the application itself, and like 1 megabyte and a half for the glibc, and everything else is the kernel. So our final results are that the CAN message is ready to be received and replied in about 360 milliseconds from power on. So we still have quite a lot of time before the deadline. Actually, we still have 140 milliseconds before the deadline, so that's quite good. And our OpenGL application is started in less than 800 milliseconds. And even if you just play with the reset button, it will be less than 600 milliseconds. So there are some stuff that we didn't try. I will still present them because I think it's interesting. We saw a patch for EDO on free-scale platforms. So basically, it will improve reading from NAND. So maybe it can be useful because maybe then NAND will be faster than the SD card. I will have to try it. Then also there was an idea somewhere, I don't remember where I read about it, but I know some people that are doing it. So the idea is to load the kernel using DMA. So basically from your bootloader, you are setting up your DMA transfers, okay? And you start it, and while starting it, you already jump to your kernel initialization. So the DMA will start to copy your kernel from your storage to your RAM, and you already start to initialize the kernel that you will try to decompress. And you hope that you won't miss. but I see a lot of people, I see some people doing that, and it's working well.
You sure they don't wait? You sure they don't wait for the end of the
Yeah, I'm sure. They don't wait for the end of the DMA.
Really?
So basically, your kernel is decompressing slower than your DMA is going, so you are almost sure that you will never try to
almost sure.
Yeah.
Very good.
Yeah, you can't know because...
Yeah, it's automotive after. Yeah.
Yeah, they're not doing that in the automotive.
Shouldn't be too hard to add logic and make it safe. All you have to do is the decompress function usually has a get no data function. So you just tell it to verify that the DMA is ready. So
yeah,
you can make that safe.
Yeah, you can make that safe. But I know they didn't do it. They just say, okay, we know that our DMA is faster than the kernel decompression, so it will always work. Always.
Until it won't work.
Until it won't work. Well, yeah, but you can make it safe if you. You can also try to reorder your init calls. So it's just a matter of linking your object another way. So you can do that in the main files. Okay. And yeah, on SMP, I saw some patches that allows you to run your init calls on different cores, so maybe it can get faster. But as I say, I don't expect that to go really faster, because actually initializing a core is quite long. It's taking like 60 milliseconds. So I have a live demonstration that is running there. Actually, it's already running, so I know that it won't. It's working. But yeah, just in case I had a video.
Slow motion.
So yeah. So the live demonstration is there. So basically, it's just the IMX6. Okay. So that's a development platform from Freescale with the SDK there. Okay. And this is the reset button. You have to believe me. Okay. If you don't know that platform, you will have to believe me. Okay. So on the screen you see the OpenGL application running. So it's running at 644 frames per second. So that's quite good. And if I reset it, then up, and yeah, that was 600 milliseconds. You can play with it if you want. If you want, I can also unplug it. It's simple. Yeah, obviously. Okay. Okay. Now, I can explain it. I can actually explain it. Okay. Because it happened when we were developing our bootloader. The fact is that that one has a 24 MHz crystal, and there is missing a resistor on that board. And so sometimes it's the crystal is ready after your CPU is trying to boot. So
It's almost sure that it's
no, but that one has a fix. But if I try multiple times, it should work. At some point in time, it will work. Ah, shit. Okay, well. Okay. If I reset afterwards, you have to believe me. So for the one in the back, I will still play the video. Okay, so that was our setup. So basically, we wanted to be sure we used the power on and the display data line. Okay, so we were basically measuring between power on, so the VDD on the CPU, okay, and display line, and we were measuring the time between we saw some data on the display line and VDD. See it? Okay, it was from power on. Okay, it's running. So that the one on the top is power. So you see that it's beeping a bit, but yeah, it's okay. And that one is a display line, and data is coming there actually when you see some noise on the line, and it's something like 800 milliseconds. I think so. Yeah, that one is 730 milliseconds. That was quite good. So, what do we want to do next? We saw some automotive customers that wanted to capture, decode, and display a video in less than 1 second. So that one will be more difficult because we know that their camera is taking at least 1 second to start. So we don't know yet how to do it. But yeah, the use case is basically they have a camera in the back and they just want to display it as soon as the user is in the car. Now we have some. I uploaded the code on GitHub. So this is the code for the bootloader. So you can see it's really small. Just basic initialization and jumping on the code. We have some patches in the kernel. They are not mainlined yet because we were actually using the kernel from Freescale, and that one is not fully mainlined yet. So we'll see. Our patches are just trying to get the kernel to compile when you are deactivating some feature. Because basically, Freescale is just testing that kernel with everything activated. So sometimes you say, okay, I don't want that feature, and then your kernel won't boot anymore. It won't compile anymore. Our main source was on elinux.org, so you have a boot time category there. Sometimes it's quite okay. Sometimes the information there is quite outdated, so you still have to try some stuff. I'll try to update it. I didn't have time to do it yet, but I will do that. For example, they are advising you not to use an intramfs, but actually what they should say is that, okay, don't use, more like, okay, use an intramfs, but use it wisely. Because we are using an intramfs and it's quite fast. So we started with only Freescale platforms. Okay, we started our bootloader, but on our side, we really feel that customers are really eager to have some bootloaders that are booting fast and not stay stuck with U-boot. So on our side, we are focusing to be as small and fast as possible. We don't really care about being generic at all. For now, we are only supporting Freescale platforms. We are also interested in TI. It will be a bit more complicated, but still doable. So if you want to join us and to write some code, that's always fun to debug bootloader. You know, you don't have anything yet. So what about the kernel? So like I said, there are still a lot of initializations that are done in U-boot. Do we want to keep everything in the bootloader, or do you want to migrate everything in the kernel? Should we do something that is configurable? Yeah, I don't know yet, but yeah, I really feel that a lot of initialization needs to be done in the kernel now. At least with the device trees are trying to do that, so that's good. So, if any of you have a suggestion for me or for that particular project, so maybe you know how to go faster or anything. So I'm open to the discussion. And if you have any question, yep.
What was the most contributor to the shrinking of the time of your 12 components you mentioned?
Yeah.
And what's most from 15 seconds?
Yeah, actually that's a bit annoying because we just did the work straight. We didn't try to measure each time, so I don't have a lot of numbers or figures to present. But yeah, I would say that at least try to start your application as fast as possible once you're in it is the one when you will, let's say, shave like 10 seconds from the boot time.
Yeah, but the first 3 seconds is most crucial. How you come to half of the second?
Don't use U-boot.
Yeah, if you don't use U-boot,
no,
then
you boot start, you boot okay, you boot finish. 3 seconds at least, 2-3 seconds. How come that half of a second? That's most interesting.
Because these demos, there's a bootloader, right? So you have the firmware, the bootloader, the Unix, OpenVG, all in less than 600.
Yeah. Our bootloader is running in 400 milliseconds. So yeah, like I said, you have power on, then you have 120 milliseconds because of hardware initialization. So nothing is done then. Then you have your first instruction of your bootloader. That's not okay. So So ours is taking like 40 milliseconds, something like that. Okay. And then you have the kernel, and the kernel is taking like 200 milliseconds. And then you have the application, and yeah, OpenGL and that stuff is taking quite a lot of time to start.
So, by the time the application is running, what interfaces do you have support for in the kernel? Apart of obviously of having video support,
Yeah.
what other interfaces are available?
On that one, you just have display. Okay. You have display, and basically you can you can also read on the MMC, so on your SD card. And then after a while, after the application is launched, you have the Toolchain driver that is working. But yeah, obviously the application is not.
All through deferred init calls, or are they loadable modules?
Yeah, that one is a loadable module. So on that one, actually, we don't do anything else than just displaying the application. But yeah, it won't take. I would say it won't take a lot of time to initialize everything else afterwards. Yeah, I would say that what's really asked by customers, at least in our case, is just to get interactive as soon as possible. So the user sees that, okay, it's working, something like that. Because I know some people that have actually kind of applications, they are claiming that they are booting in 480 milliseconds or so it's quite an achievement. And then they say, okay, we have support for this, for input and everything. But actually, input is loaded after 1 second. Because, you know, the display is coming up, and then you say, oh, okay, I will touch that. And, okay, the time you just do that is enough to load the input. Yeah, you had one question?
The 120 milliseconds, is that until the CPU starts executing from flash, or is it? Is that hardware time, or was there any software?
Yeah, it's just hardware time.
Okay, so
it just spent like regulating voltages and initializing clock, you know. Like I said, the 24 megahertz crystal is taking also some time. So
how long does it take for you to initialize RAM? Because I noticed on some systems trying to trim the data lines for DDR3 memory is really slow.
yeah, that one I don't know on that system. I don't have any.
I'm just curious.
Yeah, but it should be quite quick because as I say, we are spending only 40 milliseconds in our bootloader, and that one is setting the register for RAM. So that'll be quite quick. Yeah.
Did you use async function calls at all in your particular situation?
Sorry?
Async function calls?
No, we didn't do that. Like I said, it's something that we should definitely try.
Okay.
Yeah.
Did you ever invest time in seeing if you could optimize U-boot, or that was out of the question from the beginning?
Yeah, actually, the idea for U-boot would be maybe to try U-boot SPL. That's a small one you can, but yeah, I didn't try that. But, yeah, we just said, okay, writing our bootloader was fast enough to just do that. But yeah, maybe it can be worth a shot as trying U-boot SPL and see if it's fast enough. Any other question? No? Okay. So if you want to try the demo, it's there. So if you want to push, it's a blue button that is just there. There's a reset button. And it should work. Thank you.